Hey there. I'm Micah. I write a lot of Ruby for my day job at Heroku, and I'm also interested in distributed systems. So the sort of genesis of this is that some coworkers and I spent some time studying Raft last year, and I thought it'd be fun to try to write a simple implementation. And I've also been meaning to spend some time with Reactor, and it all sort of came together into this talk. So we're going to start with a little bit of background on Ractor and Raft. So Raptor is designed to provide a parallel execution feature of Ruby without thread safety concerns. That's from the sort of official README. It's new and still experimental in Ruby 3. It was done by Koichi Sasada, who is also responsible for Yarv, the Ruby VM that was introduced in 1.9. I actually sort of started this exercise by doing it in threads and sort of set it aside in frustration after not wanting to deal with Ruby threading problems. And when I sort of picked it up again and did it in Reactor, it all kind of fit in place perfectly. So historically, a Ruby program looks kind of like this. You have one or more processes, and inside of those processes are one or more threads. The processes shared almost nothing, and the threads shared almost everything. Now we also have a Reactor, which is sort of in between a process and a thread, and they also share almost nothing, but they're part of the same process, the same memory space, and they can communicate with each other. The code that starts running when you say like Ruby file is run in what's called the main Reactor, and it's special in a few ways. It's the only one that can access global variables, for instance. And Reactor is good for a few things. There's two big reasons. The first one is that historically, in mainline Ruby at least, only one piece of Ruby code could be running at once. You could have other threads waiting on I/O or a few other things, but only one bit of Ruby per process executing at once. It was managed by the global interpreter, then renamed to the global VM lock, and it makes it really hard to scale performance within a process. You either spin up a lot of processes and use a lot of memory, or you have to deal with this lock sort of keeping your threads from working simultaneously. So Raptor gives you one lock per Reactor, which means that it makes it a lot more straightforward to scale up. And the other reason is that it makes it a lot easier to safely write multi-threaded code. So it does this, the short version, is that each Reactor has only one way to get data into it and one way to get data out of it. And we really strictly keep track of which Reactor has authority to access which objects at any given time, so that two of them are never going to be able to change the same piece of data. This is kind of a limitation, obviously, but it's also a really straightforward and powerful way to ensure that nothing is manipulated by more than one thread at a time. It's generally called the actor model, and it's similar to ways of doing things in lots of other languages and frameworks, Go and Erlang in specific. So when a Reactor gets an object in its inbox, it's either a shareable type, which means roughly that it's an immutable thing, a frozen string or a number or a symbol. It's a class or a module. It's a reference to another Reactor, or if you have to pass something in more complicated than that, it's either a copy of the object or the ownership has been transferred to it. Raft. In the words of the paper describing it, Raft is a consensus algorithm for managing a replicated log. This means it's a way for a group of servers, in this case who trust each other, but might not be able to reach each other, might not be running at any given time, to act together to make sure that they have the same data. And that if any one of them, or in fact, if any half of them go away, you won't lose data and you'll still be able to serve requests. So it does this by having them elect a leader and having that leader making sure that each other node has all of the data that it has. That data is called a log. And technically, it's just an append-only list that only ever gets added to. But it turns out there's a lot you can build on top of that. If you sort of imagine keeping track of which SQL commands you send to a server, if you replay those against another server, unless you're doing anything fancy, you'd end up with the same data. So it's a pretty powerful building block. The sort of key part of Raft and why it was made, they said our primary goal was understandability. It's really easy to make incomprehensible systems of computers talking to each other, and Raft tries to avoid that. So it does it by having pretty distinct states that each node is in at a time, and pretty strictly limiting the scope of what it does. So in a Raft cluster, like we mentioned, only the leader can accept writes, and it only gives you an append-only log. Anything else you want, you have to build on top of it. The Raft paper is about 18 pages long. It's pretty easy to read, and I probably can't read this, but it gives you a one-pager that has really almost everything you need to know to be able to implement Raft on your own. There are other algorithms that do similar things, in particular Paxos and its family of algorithms, which are sort of infamously complicated. And then like Zookeeper and Pacemaker also like invented their own protocols to solve kind of similar problems. All right, so what are we doing? We're building a Raft cluster inside one Ruby process using Reactors. Out in the real world, you wouldn't do it this way. You'd use it for sort of distributed systems, that is, any group of computers that have to act together. A database where you wanted geographic redundancy, a load balancer where you need to make sure that all of the load balancer nodes are on the same page about which servers you can send traffic to, and so on. etcd uses Raft. It's the data store that backs up Kubernetes usually, as does Patroni, which is a like consensus proxy to help you make sure that your database clients are connecting to the database that they should be connecting to based on what's up. All right, so there's a few caveats. Reactor is experimental. Reactor is experimental. The behavior may change in future versions of Ruby. Also, there are many implementation issues. Every time you use Reactor right now, you'll get this warning. I think that Ractor is the future of parallel processing in Ruby, but that future isn't quite here yet. I think we're still learning what patterns and practices work best, and certainly I wouldn't say you should copy any of the code here and use it as the right way of doing things. Raft is not at all experimental, but this is not a full and complete implementation of Raft. We're taking some shortcuts, and I'm going to talk about what they are as we go through them and a little bit at the end. And of course, there may be errors here. The Raft paper is really easy to read. You don't need this as an implementation guide. All right, so with that said, we're going to make a cluster that has some Reactors. We're going to have them talk to each other to establish consensus about who's the leader, add some data and make sure that gets replicated, and then have the leader go away and have the cluster be able to choose a new leader. All right, so it's time for the code. Making a Reactor is really similar to making a thread. Here, we're going to make 5 new Reactors, and we're going to pass in a little animal emoji as its name. That's mostly used for debugging output. And then we have a Reactor, and we give it a block to run. So here, we're just looping over and printing out our ID, that animal name. And then our main program is going to sleep for 2 seconds. And when it sleeps, just like with threads, when it exits, all of the other Reactors that you started are also going to exit. Here's the output. There probably aren't any big surprises here. Each of the Reactors gets started. It prints out with our little log method, like the cow says, I'm the cow, the cat says, I'm the cat, and so on. So we need a bit more setup. So we have this block here. This is how you get data into a Reactor, where we anticipate getting data in. We're calling it a sender, a command, and a body, some data. And we're going to wrap it in a timeout block because it's blocks, and we want to be able to continue on and do other things if we don't have a message waiting for us. Then, with the result of that, we're going to have this switch statement, and we're going to do the appropriate thing depending on what the command was. So here we have a command. We're going to tell it to configure, that's the command name, and we're going to send it the cluster that we just made, just an array with a reference to every Reactor. Once we make all of them, we'll use this same block to send them a message one by one into the incoming queue, and you saw we assigned it to a variable so we can keep track of it. In a more conventional case, this would be the sort of thing you would have in your config file on your servers, but we're doing it this way. Okay, so a bit about how Raft elections work. In any given moment, a Raft cluster will have a term, and that's just an incrementing number. And for each term, there will be an election. And if things are working smoothly, it will elect a leader. If there's no leader, nodes are going to send out election requests trying to get themselves elected as the leader. Those nodes might vote for them as the leader. And if one node gets a majority, they're going to say they're a leader and start sending out messages to the cluster saying, hey, now I'm the leader of this term. I'll be the one sending you your data. So if we find ourselves in a situation where there's no leader, and either we haven't voted this term, or we voted, but it was a long time ago where the election might be deadlocked, we don't think we're going to elect a leader, and we're going to start a new election, then we start a new election. So we reset our election timeout. That's what we had maybe decided that it was taking too long to succeed. We're going to start a whole new term. We're going to vote for ourselves, and we're going to send each other cluster member a message saying, please vote for me for the current term. When a node gets a request vote message, it checks a few things. Is the term of the election higher than my current term? That is, like, is the node that's asking to be leader from the past, or is it ready now? And have I already not voted this term? You can't vote for more than one member for a term. If that's true, we're going to vote for it by telling it that we voted for it and sending it a vote message. And we're also going to set our own random timeout. And if we don't start seeing that there's a leader by the end of this, we think the election failed, we'll start our own election. It's important that this is random so that all of the nodes don't start trying to elect themselves at the same point, because you start by voting for yourself. If everybody does that, they're not going to be able to vote for anyone else, and you're going to be voting over and over and over again, and everybody's going to have to vote it for themselves. So if we have enough randomness that we can make it so that one person tries to get elected first, everything moves much more smoothly. If that works, we mark down that we voted. If we vote, we mark down that we voted, and we update our current term. And then this is something we'll talk a little bit about later, but in a real implementation, we would also be checking that the candidate we're voting for had all of the same data we had. And then a node knows it won if it gets a majority of other nodes, well, nodes including itself, to vote for itself. So if we see that the number of votes we got is more than half the cluster, then we decide we're the leader. We're going to reset a little bit of the state, and then we're going to send a message out to each member of the cluster to tell them that we won the election. And the way this actually works is that it uses the same method, the append method, to add data to the cluster and also to say that it was the one who won. So because only the leader is going to send out append messages, we know it's the leader. Because this system is based on us trusting all of our fellow nodes to not misbehave, all we have to do is say, append this message. There's no message, but it means I'm the leader. A node is going to get that. And if it sees that it's a new term, it says, okay, now there's a new leader. It's going to go ahead and reset some state and then make sure that its term matches the leader. Here's what it looks like. The cat is going to, well, the cat is going to be the first one to notice that there's no leader, so it's going to try to get elected. It's going to send out messages to all of the other nodes, inviting them to vote for it. They will vote for it, and it will send out a message saying, okay, I'm the leader now. All right, so we have a cluster. We've elected a leader, and we probably want to store some data. That's, certainly the whole point. So we said before that only the leader can write data or can be responsible for writing data, but a client who is trying to store data in the cluster doesn't necessarily know who the leader is. There are a few ways to handle this. You could imagine responding to a client and saying, go talk to this IP address, they're the leader. In this case, we're going to have each node forward requests to the leader if they're not the leader. So if we get a message from a client asking us to add some data and we're not the leader, we're just going to send that message along to the leader. Again, this is like a departure from a real system that goes over networks because we're not validating that the leader got it and responded to it. We're just sort of sending it to the leader and being pretty sure that it works. If we're the leader, then we have to take that message and add it to the log. And then we're going to send it to every other cluster member. And again, another divergence is that we don't validate with those members that they successfully got it and wrote it. We, have an exception here if something was going wrong, but, we're gonna say that Reactor is working correctly. If there's no leader at all, it means that the cluster can't actually write data then. You can only write data to the cluster if you have a leader. So we're gonna drop the message on the floor. You could also return an error to the client saying, please try again later. There's nothing I can do for you now. But the key thing that happens here is that we have to make sure that over half of the cluster has the data before we tell the client that it's committed. That way, if we lose half of the cluster, there's at least one node in the remaining part that still has all of the data we committed. And that is like a promise of the protocol. We're also going to complete our append method by having it actually add the data to the log. We're going to add a little message to print out the data that each cluster has. And then we're going to just start sending random cluster members bits of data to store. And then this is what it looks like. So when the leader gets a message, it adds it to the log and replicates it. When a follower gets a message, it forwards it to the leader, who then in turn adds it to the log and replicates it. And this goes on for all of the data we send in. And then at the end, we print out the data. Everybody has the same data, hopefully unsurprisingly. Okay, so this isn't terribly useful if we can't get a new leader when the old one goes away. If we're relying on one host to stay up the whole time, it doesn't do us any good to have 4 other hosts which are there and a complicated protocol about how they talk to each other. That's sort of the whole point of doing this, is that we want to be resilient against cluster members going down. So in a Raft cluster, it's the leader's job to send out heartbeats, which are also those same empty append messages we use to indicate that we won the election. And it has to do it every so often. It's just a sort of configuration. A node which doesn't get a message from a leader eventually will decide that the leader is no longer around, that it can't find it. Maybe this node actually lost its internet connection. Maybe the leader lost their internet connection. Maybe something crashed. Regardless, it's time to start a new election. So we'll just sort of delete our leader, decide that they don't exist, and then this is the same code that we had at the beginning, where if there's a node that says, I don't have a leader right now, it's gonna check its criteria, and then it's gonna try to increment the term, set a new election timeout, and try to get elected. We'll also need an extra line here to reset the timeout. So every time a member gets a message from the leader, we reset the cluster timeout. And here we're also gonna randomize it. You could imagine if we didn't randomize it, the leader falls off the network and all of a sudden everybody is trying to get elected at the same time. for the same term over and over again until you have enough jitter in the system that one of them manages to win, or maybe you would never manage that. And then we also are going to add this little message to say bye-bye and throw just to exit if we are a leader, so we can test what happens when the leader disappears. And lastly, this is a bit more about Reactor. Normally, if you send a message to a Reactor that is exited, you get this error message. You can also, if you're a Reactor, close your inbox to indicate that you don't want any new messages. Maybe you're exiting or something. So here, we're just going to catch the error, rescue it, and continue on. This is just to keep the program from raising an exception every time one of the Reactors goes away. And this is what it looks like. So we boot up. We have our first election that we saw before. The cat got elected. We start adding data, and it gets replicated through. We print it out just like before, and now we tell the leader to exit. And now nothing is going to happen for a while. Nothing can happen on the cluster without a leader, but then it times out. The nodes start noticing there's no leader, and the first one to notice, that is the one who it's the lowest randomized timeout in this case, starts a new election request, increments the term counter, sends out messages saying, please vote for me for this term. The other nodes, which are still there, note that it's a new term, and then vote for that node, and then the same thing happens just like when we started it. And we're kind of a little bit back to where we started with, except minus one node. Okay, so we have a pretty large hunk of what Raft is implemented. We have a cluster. It can elect a leader. It can store data and replicate it. And if that leader goes away, it can pick a new leader and still be able to store data and to respond to client requests. That's pretty good. And that's basically as far as we're going with Raft here. But it's worth spending a few minutes talking about some things we skipped. So if you're looking over this, you'll have like a foothold for what else there is in the protocol. So we'll go over a few of those things really quickly, medium quickly. So an important part of ensuring that you don't lose data is making sure that when you elect a new leader, they have all of the same data or more than you do. So the way that's implemented is you have a leader, when it sends out an election request, indicate how long its log is. It will say, I have had 4,272 entries, and if you have had more than 4,272 entries, then you can't vote for that leader, because that leader doesn't have all of the same data you have. And that means that eventually, the winner is going to be the node which has the most data that has been committed after the leader goes away. So the other thing is that we send along an index of the entries we're adding so that nodes can make sure they didn't miss any, because Reactor provides a ordered inbox of as the way to get data in. We don't actually need to worry about getting things in the wrong order or missing them. But again, if you are implementing this, you would want to do that. And so you just say like, this is entry number 272. And if you're like, I don't have 271, then you go ask the leader to catch you up and make sure you didn't get any, you didn't miss any. There's also some provisions in Raft for adding or replacing nodes, where you send along the whole log to a new participant, and once they're caught up, they can join the cluster, which we also didn't do. And then we talked about this a lot along the way. But if you were implementing this for real, you would actually have to make sure that you successfully sent the message, and the node that you sent it to responded that it had committed it to disk or whatever your durable storage is. There's also a lot about Ractor that we didn't go over. I wanted to mention a few things to give you a head start if you start looking for more. The documentation is pretty straightforward and not that long and pretty complete. But each Reactor also has an outbox where you can send messages out. So we only sent messages into Reactors, but you can leave messages in your outbox to be picked up. You can imagine starting a process and having results of incremental computation being sort of put in the outbox for some other process to pick up and commit it to disk or whatever else you can think of. You can also, we alluded to this, pass in more complex objects. The Ractor.send method has a move argument, and if you set it to true, it will change the ownership of that object to the new Reactor, which means only that Reactor is going to be able to access it. And if you set it to false, it will do a deep copy where it will copy that object and any other object that it refers to and any other object that it refers to all the way down. You can also specify a block with receive if. This lets you pass in a block and you'll only get the messages where the block evaluates to true. So you could imagine if we wanted to do this differently, we could have checked our inbox for all of the vote messages, handled those first. After we were done with that, we could then look at the other messages. It's like a pretty interesting way to be able to figure out what data you want in what order. And second to last, Reactors, like most things in Ruby, have a return value. This is like a great way if you just want to spawn off a whole bunch of Reactors and read their return value. You don't have to handle message passing, and it's just like a really easy way to sort of do a bunch of slow things at once and get the answer. And then this last one, I actually kind of discovered accidentally, and I couldn't find it in the documentation at all. So I wouldn't count on it. But Reactors have a Raptor local store in the same way threads do. So normally you could do thread.current and then assign a hash key to that, and only that thread would be able to access that bit of data. It turns out you can also do it with Reactors, although it's probably not a good idea. There's some unusual behavior that you're welcome to talk to me about in the hallway if you want. And it's basically like keeping something in a global variable. So I would say it is not a great pattern to rely on, but it's, maybe worth knowing about, could get you out of a jam. So all of these pieces can be put to pretty good use, building some neat stuff. I hope it was evident, pretty excited about Reactor and what we can end up building with it, and finding ways to sort of make Ruby faster and more multi-threaded without having to deal with the gotchas that I think many people have spent many hours fretting about. So that's it. Here I am. I don't tweet much and hardly ever about computers, but you're welcome to follow me. I'll have my slides and code on my GitHub eventually, but I need to touch some stuff up again. This is my dog, Haas. I wanted to thank my friends and coworkers who provided feedback. These slides are done in reveal.js, which is a great tool for highlighting blocks of code as you go. The authors of Raft and Ractor, of course. And then just lastly, please tip your housekeepers at your hotel. They work really hard. And if you have a work expense policy, it is almost certain that it covers those tips. So drop a 20 on the table on your way out. All right, thanks a lot, everybody.